Okay, so we want to talk about 2.1, number 9 and 10, maybe? All right, so what's your question, Jacob?
Well, I think I'm kind of confused at what 10 is asking for because what I think it's asking for, I already did in 9.
Yeah, probably.
That's just kind of what I wanted to clarify if I'm basically just doing the same thing over again.
Yeah, okay, so that's totally fair. All right, so let's work our way through problem 9a. Okay, so if we're going to do problem 9a, we want to compute ax by doing dot products of rows with column vectors, right? So we're going to take this column vector, we're going to kind of pick it up, twist it sideways, and slam it on there, right? So I'm going to get a times x is equal to, and this is going to give me a vector. How big is this thing? How big is this matrix A?
3 by 3.
Good.
3 by 3.
That is a 3 by 3 matrix multiplied by a, how many rows does that vector x have?
3.
Good. So that is a 3 by 1 vector. The fact that the 3's match means that I can execute this operation, and the result is a 3 by 1 vector. You guys all see that? Why am I calling it a vector and then writing a matrix? This is a weird distinction. Vectors are matrices.
I was going to say, aren't they just the same thing?
Yeah. A one column vector is a matrix.
Or you mean a one column matrix is a vector?
Yes. Both of those.
Okay. Is there such thing as a 2 column vector?
Not today.
Okay.
Kind of. Well, we'll get there. It's gonna hurt your brain when we get there, but it's really friggin' cool. I'm so excited. No, not today.
All right.
All right. So in doing this, I need to take my first row. So 1 and 2, and this is not big enough. Yeah, John, that is true. A column times a matrix is a column. Okay, so I'm going to have, oh God, why did I even start this way? Okay, so I'm going to take my row vector, right? So 1, 2, and 4. And I'm going to add multiplying by 2, 2, and 3. You guys with me on that? Out of that crap, I'm going to get a number, and that's going to be 2 plus 4 plus 12 is some incomprehensible number. 19? No, 18? Don't ask how I got something odd there. Okay. Out of the second one, you're going to get negative 2 times 2 plus 3 times 2 plus 1 times 3. So that's our row is negative 2, 3, 1 by 2, 2, 3. And out of that, we get something. 5, I think. And last one's last. You get whatever the hell you get. Negative 4 times 2 plus 1 times 2 plus 2 times 3. You should know how to do this by hand. But if you get bored and you want to use a calculator, I don't really care. Good. So I did try to make sure that you don't have too many problems where you're just doing tedious calculations over and over again. It's one of the reasons I like Strang. But if you find yourself multiplying things and it seems annoying or you've done it 4 times already, yeah, get out a calculator, do it in there. It's fine. Or Google a matrix calculator up. Let's see. So I got negative 0 out of that one, maybe, give or take. That seems weird. Is that true? 6, 8, 8. Yep. Okay, good. All right, so I got this. Now, they're also telling me that in 9a, I should have gotten, well, 2 times 1 plus 2 times 2 plus 3 times 4. You guys see how that gives me this exact same thing? So the answer here is like, check.
Yeah.
Yes. Why? Right, this was kind of Jacob's original question. Like, why in the hell am I doing problem 10 if I already did problem 9? Like, what's the difference?
For the explanation.
Yep. The difference is the perspective that I have. So when I'm looking at, if I look at AX equals B, right? So if I say let me rephrase this as, if I had the problem 1, 2, 4 minus 2, 3, 1 minus 4, 1, 2 times some unknown vector x, y, z is 18, 5, and 0. Right? This is more generally what I'm going to be interested in, right? You're not generally interested in just performing calculations. Usually you're interested in solving for stuff. You guys see that? So this is asking you to do a kind of arithmetic problem, right? You guys all on board with that? I'm not generally very interested in arithmetic. I'm much more interested in algebra because it lets me solve for things. It lets me find something out I didn't know about the world. Now, when I have a problem set up this way, I have 2 thoughts that I can have. I can look at it using the column picture, like problem 10, or I can look at it using the row picture, like problem 9. If I look at it using the row picture, like column 9, then this becomes a problem about find the intersection of 3 planes. You guys see the planes? If you do this multiplication, right, you get x plus 2y plus 4z equals 18. Right? That's a plane. Out of the second equation, you'll get something similar, right? That'll also be a plane. And then what you'll find is the point of intersection in 3 space between those. And in my case, I know what it is because I put that number in there. So it's 2, 2, 3. That's x is 2, y is 2, z is 3. That's the point where all 3 planes intersect. You guys with me on that? If I look at it from the column perspective, then it's what combination of the vectors 1, -2, -4, 2, 3, 1, and 4, 1, 2 give 18, 5, 0. You guys see how that's a different question? It feels so different. Because this is asking me, like, how do I combine these 3 arrows in 3 space? Right? Like, I need to get somewhere, and I just want to know how long I make each of them to get to that place.
Wasn't it asking how many different multiplications of it get you there? Not necessarily.
Yeah, what combination? So in other words, how do I scale each length to get to, like, you know, up here's my, like, secret spot that I need to get to, and I have these 3 directions that I can, like, adjust the lengths. And somehow that answers the same question as where are these 3 planes intersecting. That is mind fucking boggling. And yet it works. You guys see that?
Mm-hmm.
So times when I'm interested in questions like what combinations of these give that, this is the drive behind machine learning. Like when you're, you know, when you pull a phone out and it's recognizing people's faces, like that shit's all about which combinations give this vector. Whereas like construction problems are often about finding the intersection between three planes, right? Like if you want to know how many tables can I make at my factory, that's going to become a question about intersections of planes or lines or something. You guys see how those are pretty different approaches? But they use the exact same set of tools. Did I somehow get your answer in there, Jacob?
Sorry, I was distracted for a moment.
No worries. So one's about how many of these, right? That's like a weights question. That's like a machine learning kind of problem. Like which of, like how many of these do I need to push on, right? So it's actually calculating weights that makes facial recognition softwares work. The other thing about finding intersections of planes is more like how many tables do I make with this, with this specific set of raw material, with this amount of raw materials that I have. But somehow we just use the same tools and everything works out. Does that kind of make sense?
Yeah, I suppose.
It's fair if it doesn't. This connection is super surprising.
I mean, I get how the intersection of planes relates to matrices and all that. I guess maybe I just didn't see that last little question at the bottom. Maybe that's why I was confused.
Oh yeah, so this sort of separate question is, so for how many separate multiplications do you need to calculate a times x when the matrix is 3 by 3? Well, I can pretty quickly see that there are 9 multiplications, right? And how many additions?
Sorry.
Why do I care? Do you guys ever find that your computer runs a little slow doing certain things? Do you ever wonder why certain tasks take more computational power than others? Do you ever wonder why whenever you have too many Chrome windows open, everything else stops working? That's because Chrome leaks memory like a sieve. But the other things are usually related to the complexity of the task that you're doing. And so we're pretty often interested in the computational complexity of a task. So in this, knowing that that multiplying a matrix by a vector takes 9 multiplications and 6 additions is a kind of thing that I could use to think about how much power is this going to consume? Should I task 2 processors to this or 3 or whatever? You guys see that?
Mm-hmm.
Okay, good talk. All right. Anything else?
Not for me.
Can we do 1.31?